Hello everyone, and welcome to this month's Practical Stats webinar. We're going to be talking about trend analysis for data with Nondetects. Let's go ahead and get started. This is trend analysis for data with Nondetects, and we are going to talk about methods for doing trend analysis. So, what are we trying to do today? I want you to see why substituting in numbers should never be done for trend analysis. This is like the worst case for doing substitution of numbers like 1/2 the detection limit. So you're going to mess it up if you do that. So let me see if I can convince you of that. Second, we're going to talk about what is possible for doing it without substituting in numbers like 1/2 the detection limit. And we are going to be looking at 6 different methods for doing trend analysis. So I'll give you an overview of how they work briefly. And another objective, at least for me, is to show you the kinds of things that are in our Nondetects and data analysis course, which there's obviously a lot more detail in that course. So why not put in 1/2 the detection limit or something similar? The commonly substituted values, 1/2 is used in water quality for whatever reason. Someone decided a long time ago that, oh, I don't know where it is between 0 and the detection limit, so 1/2 ought to be as good as anything else. And it is as good or as bad as anything else. The air quality folks use 1/2, I think back in the 1970s or 80s. There were some people at the USGS that said, you know, we have data that look like a log normal distribution. Our data are skewed. They were dealing with trace elements in soils, I believe. And they said with something like that, 1/2 was better than 1/2. And they had reasons for that. I'm not sure that I buy into it, but it's no worse than 1/2 either. They're both pretty terrible. So why are they terrible? Because they put in what I would call invasive data. It's data that you've just made up. It's alien to the concentrations you actually measured and had single numbers for. So you're putting in not just one number and not just 1 or 2 numbers, but you're putting in a series of numbers. And if they're all the same, that's a pattern. And it's a pattern that the trend analysis procedure will see in a certain way. So it's going to produce poor estimates of things like standard deviations. Why do you care if you're doing a regression type of trend analysis? Standard deviation is really important. It's going to be the noise level that tells you, can you see a trend above that noise or not? If you have changing detection limits, then that's going to stick in a pattern that's going down or up, usually down over time. And so the result is poor estimates of slope, incorrect p-values for the trend tests, and all of that is not necessary because there are very good methods for doing trend analysis without putting a number in for Nondetects. So here's just some examples. This was data that is in my book on this topic, and it was basically a straight line with some noise. So it was generated. It has a correlation coefficient of 0.8, so that's a pretty strong correlation. And what if about half of these turned out to be Nondetects? So I just changed them with 2 detection limits at 3 and 1, and then stuck in 1/2 the detection limit. And what do you see? You see, for all the Nondetects, you see flat lines, 0 slope lines. That's a pattern. It's not neutral because that pattern looks very different than the original pattern of the data. It lowers the correlation down to something like 0.5, probably not significant. So you've just changed the answer because you put in the same number all the time. So that's certainly not a good procedure, and it's one of the classic ways of not finding a trend that is really there. Also, it's possible with substitution to find a trend that is not there. So here's also data generated. It's just random noise, random data from a normal distribution. And there's no correlation. Kendall's tau is 0.11 and the p-value is high, so we would not say that there's a correlation in this set of data at all. And we're going to look at where the X values are going to be time in trend analysis. That's basically a definition of trend analysis, any analysis where one of the explanatory variables is time. So suppose we had 23% of the samples, which is what I did, but just roughly around a fifth of the samples had higher background salinity. Well, I'm making that up, but that's one of the causes of changing detection limits. At least in the Western North America, some of the groundwater in the West is fairly saline, and people in the lab have to dilute that in order to run it through the equipment. And so that changes the detection limits. If you're dealing with organics, lipid content kind of has a small but persistent signal throughout a wide variety of wavelengths on a chromatograph. So it interferes with all kinds of organic compounds. So if you have high lipid content versus low lipid content in the sample, changes the detection limits. If you're dealing with solids and you collect things like leaves and there's not a lot of it, and you submit that to the lab, if you send them a sample that has a lot of mass of that, several grams, let's say, then you might get a smaller detection limit than if you send in only a few leaves. So the detection limits change, that's the main story, as a function of things that have nothing to do with what you're trying to measure in the sample. And on top of that, because of better equipment, detection limits tend to go down over time. So here I've put in a signal of 10 to 7 to 5 for the detection limits. And then I used 1 over the square root of 2 just to be different. And so the red dots here that you see are the non-detects going down over time, but now they are less than 10 and less than 7 and less than 5. And I've put in 10 over the square root of 2 and 7 over the square root of 2 and 5 over the square root of 2. So that creates an invasive downtrend, one that was not there in the original data. So one of the classic cases of finding a downtrend in particular is when you have non-detects and you stick in something like a half of the detection limit or whatever your favorite fraction is, and that goes down over time. And that has nothing to do with whether the original data in the stream or the aquifer or in the soils goes down over time. And so you create a correlation of Y, what I guess it would be concentration versus time, and this becomes significant with just this fairly small, fairly modest amount of censoring of 20%. So we get a p-value of 0.04 and say that there's a correlation. There's a significant trend, a downtrend, when there's not. So you can find a trend that's not there. And this is just a summary slide that just says that you can turn a data set with trend into one without by substitution. You can turn a data set with no trend into one that has a, quote, significant trend with substitution. So that's why it doesn't work. That's why you need to do something better. When I was a young lad, my grandfather used to quote to me all kinds of fairly short poems that he thought were interesting. He liked mental kind of things, things that had a unusual ending or things like that. And this was a limerick that I remember that he quoted to me when I was young. And I have put it in my book, but I've never used it in a talk before. So here it is. That yesterday upon the stair, I saw a man who wasn't there. He wasn't there again today. Oh, how I wish he'd go away. And that's what you're doing with substitution. You're putting in a man who's not there. Or perhaps you can't see the man that is there. And so you can get confused very easily. We don't want to do that. All right, so what is trend analysis? The topic for today. It's where there's some Y variable plotted on the vertical axis, and then X axis, there's at least one X variable that is time. So we're looking at changes over time. Today, I'm going to talk about time continuous, where you're measuring things like every month or every quarter of the year, something like that. And so you would like to know is, are things changing? Are they generally going up or generally going down, or neither of those? So the null hypothesis is that there's no change over time, no signal, no general increase or decrease. I will mention that that kind of question, is there an increase or decrease, that's a frequency question. It has nothing to do with something called the mean. And so it's really asking, are higher values more frequent at the end than they are at the beginning? Are low values more frequent at the end than they are at the beginning? So that's a clue that non-parametric tests that deal with frequencies would work generally better to answer that question. People do use means. They do use regression, which is just a linear mean. And to the extent that that describes the middle, you could also use that for trend analysis. So you're going to have to do things to make sure that the mean, the regression line, is actually in the middle, which means you don't have a lot of outliers and you don't have a lot of skewness. All right, and so the alternative, if you reject the null hypothesis, is that there is a general trend here. And oftentimes there are other things like the effects of other variables that are not time, things like stream flow or depth to water in a well, or seasonal variation, patterns that year after year are generally higher in one season and lower in another season, things that reflect temperature changes or precipitation changes that are commonly occurring every year. So we're going to deal with those as well today. All of those things, the things that are not time, obscure. They have noise and they obscure the trend signal, and you often have to pull them apart in order to see the trend. So we're going to look at 6 different methods today. Starting in the left-hand column, it's where time is the only X variable. So this is the simplest procedures. You can look at Y versus X, where X is time, with regression. And we're going to do a version of regression for censored data with maximum likelihood estimation. And again, the correlation and regression webinar of several months ago gives you more detail than what we'll do today. The non-parametric version of that is something called the Akritis-Thiel-Sen test, and it's a version of the Thiel-Sen procedure that computes a straight line, and associated with that is Kendall's tau correlation. So these non-parametric methods, the test for trend is there a correlation of Y versus time, done by Kendall's tau. And so again, it's just Y and one variable for the X axis, and that's time. So that's simple. Now I'll introduce in the middle column here another X variable that's not time, call it a covariate. And it is covarying with time in the sense that it's going up and down, and it's going up and down and moving the Y variable concentration, the thing we're trying to look at for a trend in, moving it up and down as well, and that produces noise. So we're going to try to split out the effect of this covariate, this not time variable, from the time effect. And in regression, you can just do that as multiple regressions. So we're going to have Y, this Y sen is the censoring indicator, a 1 or a 0, and I'll tell you about that in a minute. And then now a series of X variables. In this case, I'll just use 2, some time variable, and I think I'm going to be using flow, mean daily flow, for the trend analysis in this stream in the data set. And so you just put them in as 2 X variables in a regression equation, a multiple regression equation. Sounds simple. It's just solved by by maximum likelihood estimation. And then you can do something similar to that in a non-parametric fashion. Non-parametric methods are no model methods. They try to avoid modeling. And so we're not going to really do a model, but we're going to do an extraction of what's left over after you account for the relationship between Y and X, where X is not time. So we're going to use something to relate to that covariate, subtract off that covariate effect, and then run the ATS trend test on the residuals. And in red here are the names of the functions in R that I've written that will run these, and they come as part of the Nondetects and data analysis course. So there's a send trend function for what I just said. In the right-hand column is parsing out the seasonal variation. And so the regression approach is to add two new variables, the sine and cosine of something. Those just go into this X frame, this matrix of X variables. Now there might be four variables: time, stream flow, and then this sine and cosine terms. So that can all be done with regression. And then the non-parametric approach is something called the seasonal Kendall test, which I think many of you are probably familiar with, developed at the USGS in the 1980s. And what it does is just to look at the ATS kind of procedure, the Kendall's tau-based procedure within each season separately, and then combining all of those seasonal results together into one total. So all of that can be done for censored data, data with non-detects. Censoring just means in statistics that you're above a threshold or below a threshold, and you don't know the unique value. Statisticians have been using methods for censored data for decades, but we are not as familiar with them in the environmental sciences. And there's one here for doing the seasonal Kendall test with censored data. Okay, so let's start out with the regression-based approaches. We are going to do maximum likelihood estimation, or MLE, or we're going to let the computer do it. How does that work? It starts with the observed data. It says, given that data, what are the slopes and intercepts that are most likely to have given rise to these data? In fact, let's boil it down to the one slope and intercept pair that will likely have given rise to these data. And that will be the maximum likelihood estimate of a regression slope and intercept. So there's two types of information that are utilized. And if you'd like more information on this point, you can go back to the webinar that's up on our page that we did back in the spring, I think, which is how the mystery of non-detects and how non-detect methods work. But basically all these methods for sensor data use two types of information. First, the values for the detected observations, just as you would with any other procedure. You've got those. And then for the non-detects, the observed proportions of the data below each detection limit. And how are these things changing over time? So with the observed proportions, let's say your detection limit was 10, and these work just fine for multiple detection limits, but let's say you had one at 10, it would look at, well, what proportion of data are below the detection limit in the early period, say in the first couple of years, and maybe there's 50% data that are non-detects less than 10. And then as you go on in time, now they're down at the end of the time to about 20%. And so generally there's fewer non-detects. That's evidence for increasing concentrations. So it's using both types of information to judge whether the slope is going up or not, whether it's zero or whether it's going up or whether it's going down. And we're going to assume, because this is regression, that the residuals from the regression have a particular distribution. So it might be a normal distribution. Most of the time with environmental science, you'd be picking something that was skewed, more like a log normal distribution. So we'll choose one of those. And so this is an optimization procedure with maximum likelihood. It's going to compute this thing called a likelihood function L, which is just a measure really of the mismatch, the error between Y, the observed data, and then the model, the B0 plus B1 times X. And so it's going to do that for a variety of intercepts and slopes plugged in and see which ones have the best L. And this L is going to be a negative number. And in the best case scenario, if there was a perfect regression equation with no error, it would have a value L of 0. So you're trying to get it as high as you can. And so you pick the peak here at the top, and that's going to be the intercept and slope from an optimization. That is the intercept and slope that were most likely to produce the data that you observe. And that data looks like both the detected observations, which are the gray bars here, and I've just fit a nice log normal distribution to this. It's the going through kind of the middles of the tops of the gray bars. And then it's also trying to match the proportion of data here on the left side that are below the detection limit. This detection limit is 0.02. And we observed in the data 55% that were below 0.02 overall. And at this would be at a slice of an X value at a time, particular time. And at that time, we observed 52%. So that's pretty close. So this optimization is trying to match both of those things, the detected concentrations as well as the proportion of data below one or more detection limits. So that's maximum likelihood. So with any other regression, you would do these steps. You'd first check for multicollinearity. If you don't know what that is, go back and listen to that correlation and regression lecture, but it's basically the correlation among the X variables. With one X, just time, we don't have to deal with that, but when we start adding these others in, we will. And then use the regression procedure to compute the equation, check the residuals to see that they follow the distribution that you've assumed. And then there's a statistic, which is a really excellent way of looking and deciding what is the best model, called AIC. And so you'd pick the model with the lowest AIC. AIC is a measure of error. And you can use that among models that are different sized, have different X variables, or that are disjoint, totally disjoint, so that the X's in one model was X1, 2, and 3, and the other next model was X5, 6, and 7. Totally different X's. You can compare their AICs. So it's a far better method than R-squared. And if that you're not familiar with those things, our basic course in applied environmental statistics goes over them in detail. Or get a good book, get a recent book, get a book that's been written in the last 20 years on regression. Okay, so I'm going to use a data set of total recoverable chromium concentrations that was donated to me by a colleague. And I've tweaked it, so it is not the same as what was given to me, so you can't go back and say this is what happened in the field. I did that on purpose. I also did it because there was a little bit too much flow information that was not there for some reason. So I put some in. And I think I put values in that were pretty consistent with the pattern in the rest of the data, but who knows? So anyway, that breaks up that pointing fingers part. So what you have are the concentrations. There's also an indicator variable. I've named it CRND, but if you've done any of this type of procedure before, you're familiar with this. This is one of two basic ways of storing data that are censored in a data set, and that's to have a second column that has an indicator. I use ones and zeros. One meaning a detection limit is back in the original Y concentration column. So if the detection limit's 0.02, there's a 0.02 back there for that row in the data set. And the 1 tells you it's a less than 0.02. If there's a 0, it tells you that what's back in the Y column is the detected concentration. So there might be a detected 0.08 back there in the Y column. So it tells you which are which. There can be multiple detection limits. Doesn't have to be the same number in the Y column. So it's a fairly flexible, I would say it's the second best method of designating these things. So you can perform a regression kind of jointly. The Y variable and this indicator are the Y variables. And then X is this thing called decimal time, dec time. I'll give you an example. So you put this in the XenCore reg procedure. This is all done in R software. Maximum likelihood regression with censoring is in almost all commercial software. You would look in the survival analysis sections of those software packages. And so this procedure gives you back AIC. This is 96.4, just around it. And there's no good or bad AIC. It's a function of how many data points there are and how many pieces of error you're summing up. So 96 is what it is for this data set. What you want to try to do is say, is there a better model, one that has a lower AIC? It gives you back a slope for decimal time in this square to the left, minus 0.059. That's the slope times time for the log of chromium. The default in this and most of the censored procedures in R is to take the log because Almost never, when you have detection limits, you're down close to zero. If you're down close to zero, it's very unlikely that your data look like a normal distribution, because you can go a lot further away going up than you can going down, unless you can go negative. And the things that we measure usually do not go negative. So they're not going to be symmetric. They're not going to be a normal distribution. So logs of chromium as a function of decimal time, there's the slope. So it's going down 0.06 log units per year. That's about a 6% decrease per year. Here's the p-value. It's very small, so it is significant. It's not just noise. So we do have a downtrend in this data. You can check the normality. It's right at the threshold, 0.05. It's slightly above 0.05. So that would, if you were a strict slice with a razor at 0.05 person, I'm not, but if you were, you would say you would not reject normality. And this is normality of the logs. It's a test for a log normal distribution. So you would not reject that. And it's so straight that, yeah, you probably could work hours and not find a better distribution to fit this data. So that shows you that's pretty good for field data. That's not a huge departure. The departure's up at the upper end. There's 4 or 5 outliers. So this would be a reasonable model. Okay, so that's the individual one. How about if we bring in another X variable that's not time, you put that into what's called a data frame, which just means you've got a name to it that is for 2 columns of data together. So decimal time and the mean daily flow. And so put those in as 2 X variables, you get back an AIC of 63.5. It was, what was it, 90 something before? Yeah, 96. So that's a pretty huge drop by 1/3 or more. That's a big difference in AIC. That's telling you that that daily flow variable is really important. It's modeling a lot more of the variation than just time alone. And it's going to be significant. And this is going to be a much better model. The 2 variable model for 2 X variables is much better than the 1 variable model would be. It gives you back the individual slopes. Here's the one for decimal time. Again, it's a minus 0.05. Yep, minus 0.05 log units per year. And it's significant. And then the very significant one is the mean daily flow with a positive slope. So chromium concentrations probably adsorbed to sediment is being pushed off at a higher amount at higher flows. And that's important to take into account. Oftentimes this adjustment is because we'd like to say what people are doing. Maybe in this area there was some control. I don't know that to be true, but some attempt to try to decrease chromium. And if so, all of the things that's just due to flow, all the up and down in concentrations because the up and down of sediment concentrations with higher flows is noise for the trend test. Putting that mean daily flow in the regression equation takes out that noise. It models it, it accounts for it. It subtracts it, if you want to think of it that way. And this slope would be the slope that's left after you, quote, hold flow constant, unquote. So we're trying to meet that goal. And then, so usually you're trying to subtract off something you cannot control, like some climate variables, so that you can get to what humans have done. Maybe there was some attempt to decrease output of chromium from somewhere. Or maybe just to cut down sediment, I don't know. Anyway, we do find a downtrend, a significant downtrend once we've accounted for flow. And it's not uncommon to not see a trend with that just 1 variable model, and that you have to use this second variable, the flow or the depth of water in a well or something else, precipitation, that is correlated, and you know that by science, correlated with the Y variable so that you can remove that effect. All right. So you can check for what's called VIFs, which is the correlation among the X variables. I won't go into that, but you want values less than 10, and we've got them down at 1, which is the minimum. So there's no multicollinearity, no correlation between decimal time and mean daily flow. So that's good. That would mess up a regression equation and make you think that things are not significant when they might be significant. That's why you worry about it. If you want more information on that, see the webinar from a couple of months ago on correlation and regression. Okay, and you can do the residuals plot from this 2-variable model, and now the p-value is quite a bit higher. A lot of times the non-normality that you see in these probability plots or QQ plots really are caused by other variables you have not yet put into the regression equation. So this one makes it closer to a normal distribution. These outliers in particular are not real high because that high value was because there was a high flow, probably. So we've subtracted that effect out. So this looks very much like a normal distribution in terms of that p-value being much higher than 0.05. And so we would say this is a good regression model. Finally, seasonal variation. You'd add in 2 new coefficients, sine and cosine, of 2 times pi times time, where time in this case is in years. You're going to get one wave cycle, one thing that goes, let me do it this way, up and then back down and back to where it started from during the year. And the slope coefficients on these 2 terms, sine and cosine, will fit that wave pattern to where the peak in the year is observed. So if it observes in the spring, it'll fit it there. If it observes that peak in the fall, it'll fit it to there. And it's doing this with one cycle for whatever 1 units are here. So T here, if we do it in decimal years, decimal time, at like 1997.5, that would be about the end of June in 1997. It's really ignoring the year. It's just using the fraction of the year and saying, where are we in this circle when we go around the year? We start off here January 1 on the right and go around, and by the time December 31 hits, we're back where we started from. And so that's the 1 cycle per year model, going around the 2 pi circumference. So we do that by putting in 2 terms, the sine of 2 pi t and the cosine of 2 pi t. This is an old, decades old way of modeling a seasonal variation. And the coefficients for B3 and B4 here, if they're significant, then there's seasonality. If they're not significant, there is not. And the magnitudes of them are fitted so that it fits the pattern in the data. You need to keep them both. If one of them is significant, I would tell people to keep them both. Or a better way is just look at whether the AIC is lower with them as opposed to without them. So we can compare this model, which has 4 X variables, to the previous model that just had time and flow. 2-variable model. And if the AIC for this is lower, then this is better, and there is seasonal variation. If AIC is higher, it's not better. Adding sine and cosine actually makes it worse. It's a worse fit, and there is no seasonal variation. So we do this real quickly. The AIC is higher. It's 67 instead of 63, and there's not going to be any seasonal variation here. The VIFs are all good. The slopes are significant for decimal time and mean daily flow. They're not significant for the sine and cosine. That's not surprising given that AIC. So we would say there's no seasonal variation other than that one that is inside of the flow pattern. So we don't add additional terms. So that's the regression kind of approach. All of those were done without substituting any numbers for Nondetects. They just looked at the proportion of data below each detection limit. Now we're moving into the non-parametric, the percentile world, the frequency world with the Akritas-Thiel-Sen line and Kendall's tau correlation. So this line has a slope and an intercept. The slope is the one that if you subtract it off, take its residuals, it would have a Kendall's tau that's as close as any of them to 0. So it's got the best fit of a 0 slope line after you've subtracted off the slope for the ATS line. So it's another optimization procedure, has no distributional assumption built in though. That's the difference between that and maximum likelihood. The test for the slope being equal to 0 is the test for the Kendall's-Tau correlation of data versus time. That's the trend test. And you can read some more about that in this book, which I wrote back in 2012. This was the second edition of my Nondetects book called Statistics for Censored Environmental Data using Minitab and R. And the examples come with both R and Minitab worked out. And that tells you about the ATS procedure. And so if you do that just with 1x, which is decimal time, it would look like this, where you have the y variable, then the indicator for the y variable, then decimal time. I start out usually with saying log is false. The default is that it's true. I don't really like that default because this is a non-parametric method. It's not going to be affected by a couple of outliers. So the question is really whether the patterns are straight or not. This is a straight line fit. If the data are straight, let's take a look at it here. This is the data plotted with the outliers up here versus time. This is a fairly straight pattern going down at this bottom part here, and it's just these 4 outliers at the top. That was the necessary reason to take logs with regression. So there's no motivation for doing that here. So I start out without taking logs and look at the plots, and then if it looks like it is curved, if I take logs, both regression and this line will be straight in log units, which means they're going to be something like a exponential decay here. They're going to be a curve in the original units. And so to keep it simple, if log is false works fine and it looks like a straight line, then you've got a slope that instead of percent per year is micrograms per liter per year down. So this is going down about 0.04 micrograms per liter per year, and it is significant. So that's the ATS approach. There's no substitution. It's just looking at the ranks of the data that are like less than 1 and a 0.05 or a 0.5 even. All of those are tied with each other when Kendall's-Tau is computed. So it accounts for what you know and what you don't really know. Like, is a less than 1 different than a less than 10? You don't know that, and so those are tied in the Kendall's-Tau procedure. And in this data, it was plenty evidence to say that there's a downtrend. Notice on these plots, which come out with the procedure, that the dashed lines here are the non-detects, so they're drawn from 0 or some low number up to the value for the detection limit. And the non-detects actually occur mostly in the later years, and so that's an indication that things are going down. And that information is used in this procedure, along with that the data, the detected values, are also going down. Both of those are data telling it that it indicates a downtrend. So the decision of whether to take logs or not, whether this is a curve or not, is up to you. And just base it on what the plot looks like. You would get the same Kendall's-Tau and the same p-value whether you took logs or not. So it's not an effect of the test, it's only going to affect the model, the predicted value of y that you get. Okay, so now the second non-parametric method was where we were going to adapt the procedure for a covariate, for a not time variable, in this case the mean daily flow. And what we want to do here is to model the relationship between y, the concentration of chromium, and mean daily flow, and then subtract that out. And once it's subtracted out, then we do a trend test on what's left, the residuals. So we're going to subtract it out by using a smooth. Why do we use smooths? Because smooths don't have a formal equation for them, which means they're not restricted to being a particular shape. They could go up and come back down. They could be a straight line, but they're not necessarily one. They could be a nice curve. So the smooth just is a very adaptive, non-model approach to modeling the relationship between y and x, and then getting rid of it so that we can see if there's a trend in what's left over that's not explained by the relationship with flow. So here's a picture of that smooth. This is kind of a red or orange line. And you can see it's not a straight line. It does curve, it goes up. It's pretty close, but it's not a straight line. It's bending up at the upper end. So this was the smooth, the chromium versus mean daily flow, and this is the plot of those things. Then the residuals, the difference between the points, including the non-detects, because there's some smooths that work with sensor data, including the non-detects, and the red line. That difference is the residuals. Those differences are taken over and run in the ATS process. And that's all done with this send trend function. So here's the residuals from that smooth, the ATS line that's fitted to it, the effect of the non-detects as well as the detected values. Kendall's tau is again negative, and the p-value is 0.03. So some of the downtrend that was there in the original data, it says, was subtracted out with the flow, that there must have been a trend of some sort in the flow, because it was a 0.00 something before. Now the p-value is 0.03, not as strong, but it's still significant. So there is a downtrend, even when you account for the effect of flow. Finally, the seasonal Kendall test computes an ATS line and a test for each season separately. So what the seasonal part of the seasonal Kendall test does is it does not make comparisons between data in different seasons. So the idea here is that you might say, well, it really doesn't make sense, or it's not fair to say that there's a downtrend or evidence for a downtrend when there's data going down from the spring to the fall, because in our watershed and in our general area, spring tends to be high concentrations for whatever reason, and this fall tends to be lower concentrations. So the fact that you're just going between those seasons is not really telling you whether there's an overall trend, if year to year to year there's a trend. So what you do, this is something called blocking in statistics, is just say, well, I'll split the data up by season and do the test individually in each season, and then somehow in a smart way combine it all together for one overall consistent trend. So the seasonal Kendall test is going to look for consistency. If it shows an uptrend in one season and a downtrend in another season, those can easily cancel each other out. And so there's no overall significant seasonal Kendall trend. It's looking for consistency. And it does the test by comparing all the data within the same season to one another and runs the ATS procedure. It does not compare data across different seasons. It gets an S statistic. That's the test statistic for Kendall's tau. And it gets one for each season. And then it sums it up to all of those seasonal S statistics to get an overall seasonal Kendall S statistic. That's hard to say. So S is just the number of pluses minus the number of minuses. What's a plus and a minus? The number of pluses are the increases as Y increases, so that there's a pattern that is in the same direction between Y and X. So Y is going up as X goes up in time in this case. And the minuses are the opposite. So the pluses would lead to a positive correlation. The minuses would lead to a negative correlation and a downtrend. And so the S is there some pattern in the data that doesn't look like it's 50-50, because if it was just chance and there was no trend, about half of the data would be going up and about half the data would be going down when you compare from one day to the next, or 1 month to the next, or whatever your time units are. So when you get done, you have an S for each season. The little I here, subscript, is the season. Sum those up and you get the S overall for the seasonal Kendall test. And so here's the output for this data set. There were 2 seasons not defined by me, so I can't really tell you how it was done. But one was the dry season, one was the wet season. And you see here with a Kendall's tau of minus 0.3. Again, Kendall's tau is about 0.2 less than Pearson's R, so that's like a minus 0.5 of Pearson's R correlation. This is a moderate correlation for Kendall's tau, and it's a significant non-zero correlation. That's what the p-value tells you, that it's not 0. In the dry season, the chance of getting it just by chance is 9 out of 1,000, 0.009. So there's very little chance that you'd be getting this when there is no trend in the dry season. So we have a downtrend in the dry season. There's a negative slope and a negative tau in the wet season, but it's not very strong. The p-value is not significant. Here's S minus 176. There's much less S. It's much closer to 0, minus 24. So it's more like there's just as many up increases as down decreases. The minus 24, add those together, you get the minus 200 for the overall seasonal Kendall test. That's a p-value of 0.014. So there is a trend. So they're saying that there is a significant slope, and it gives you that slope, which is just one of those ATS slopes of a minus 3.6. That should be 0.036. Excuse me. Should have caught that one before now. A minus 0.036 micrograms per liter. I guess I could change the units to something else, and then it would be minus 3.6, but it's minus 0.036 micrograms per liter. And you can get the overall line. To get a picture of it, you've got the equation for that overall line. There's one interesting thing, to me anyway, that with censored data, it's really hard to estimate this denominator, the variance of S, with some numbers that you only have a threshold for. So unlike maximum likelihood, that's difficult to do. What is not difficult is to run it as a permutation test. And so if you heard the permutation lecture from a month ago or so, these are a new class of tests, not parametric. They are, in a sense, well, they definitely are distribution free. That's one advantage of them. And another advantage, and that's the one in this case, is that they can compute tests for things that you really don't have a unique formula to compute it with. So this formula was for the seasonal Kendall test without censoring. Now I'm going to just do it as a permutation test. So here's an illustration of what's going to happen. We're going to take thousands of times. I'm only going to do 20 of them, where you rearrange the X variable. So we're going to rearrange the time variable and just randomize it. So you're totally breaking up any correlation that is there between concentration and time. And then each time you do this, and that's just done with random number generators, when that's done randomly, rearrange the order of time here, then you compute an S for each one. So those thousands of S's, that's the test statistic, S, those 1,000 of them is a picture of the null hypothesis. It's a picture of the S values you would get when there's no correlation between Y and time, because you've broken it up by randomizing it. So let me click this, and you'll see this happening, again, about 20 times or so. It's going to be hard to see, but what you can probably see are the dashed lines changing. There they go at the bottom each time. You can see that the slope is changing, the line is changing each time. That's just randomly rearranging the time variables and then running this. And so you're rearranging where the data are plotted, the points are plotted each time. Each time you get an S statistic. And so this is just a picture of what's happening when you're breaking apart that correlation between Y and time. These S values are all the values that you would expect when the null hypothesis is true, and they're in the frequency that you expect when the null hypothesis is true, and you can plot those as like a histogram here. So this is, I think, 1,000 S values. And then you ask the question, which is the basic question in statistical testing, how likely is it to get the value that I got from my data, in this case, minus 200, when the null hypothesis is true? And it's just the number of times, so it's easy to count. The number of times you get a minus 200, that's this dashed red line, or something more extreme, so more negative, plus the number of times you get a positive 200, so same magnitude of trend, but now an uptrend, or something more extreme, so more positive. So the number of times you get S being greater in absolute value than 200. And apparently in this data set, there were 14 of those, including the one time that your observations are. So 14 out of 1,000, so 0.014 is the p-value. So that's a permutation way of doing a p-value. It means you don't have to compute a specific equation. And this was the way that statisticians really envisioned the way statistics was working back in the 1930s, but they couldn't do it. They didn't have the computer capabilities that we do now. So that's the permutation test for the seasonal Kendall test. You can get back plots of the individual seasonal slopes, etc. You can see that this one doesn't look very different than 0, and it was not significant. This dry season does look like a downtrend, and it was significant. So in summary, you should not substitute values. You can cause all kinds of errors by substitution. You can find things that are not there. You cannot find trends that are there. And you're putting in a pattern. That pattern depends on the characteristics of the data that you're sending to the lab and what the lab does with that, including method changes in the laboratory and how that's affected detection limits over time. So especially for trend analysis, it's a really bad idea. There are excellent methods for conducting trend tests with sensor data that do not substitute values for non-detects. Parametric methods are based on maximum likelihood regression. You can find those in any commercial package, including R, which is a commercial one in the sense that it's managed by people. It's free. Most of the commercial packages are not free. Non-parametric methods are based on Kendall's tau and that ATS line, the extension of the Thiel-Sen line to sensor data by Michael Akritis and students, I believe. So those are all available and they are found in our course. That's where the scripts are anyway. All the methods are done with code that's in R itself. You'd be using things like the survival package in R and the NADA package, NADA package in R. So that's those. And so first, thank you for being here today. I have run out of time. I will stay for 10 minutes and do some questions. How to handle situations where your covariate also changes with time. That's a great question. Well, there are fancier mathematical ways of doing it. I don't know that anything, it's definitely the non-parametric methods I talked about today don't really do that. It is assuming that you've got this stability so that you've got this one smooth or one slope in regression. So actually both of them depend on this. Both of them you can describe that relationship kind of uniquely that doesn't change over the time period that you've measured. So you'd have to do something fancier, at least in a modeling situation or in a smoothing situation. That particular situation, Bob Hirsch, is a colleague of mine for many years at the US Geological Survey, has put out a package in R called WRTDS. And it doesn't try to do hypothesis tests, but it does try to do a lot of plots. And it does smooths in a way that you can parse out which changes are due to flow and which changes are due to time, and then how does flow change over time. So at least in terms of diagnosing that the problem is there, that WRTDS package would definitely be worth looking at. It's really a nice package. And it does a lot of trend analysis, but not with p-values for the most part, but with plots so that you can understand what you've got in your data. Can you explain how smooth is calculated, James? Yes, I can. I don't have time to do it today. It is described in the course. It's not in that 2012 book because I wasn't doing it back then, but it's something called a GAM, a generalized additive model, GAM. And that's a regression type of smoothing procedure. It does allow you to do it with a base of censored regression though. So that's why I use it, because it allows the censoring. In the Applied Environmental Statistics course, which is the course I've taught for decades, we have always used the low S smooth, which is a very simple smooth, but that's not really something you can do with censoring. At least I've not seen it done. So these other types of smooths you can do with censoring. So whatever you pick to use, you want to make sure that you can get that proportion of data below detection limit information in order to affect the results of the smooth. Okay. It's one that says Gilbert indicates some missing data are allowed with the Kendall's test. Is there a way to assess the effects of missing data? Yes, Gilbert took the original papers by Bob Hirsch and others and put them into his book, but then I do the same thing, so I can't complain. And yes, these Kendall-based procedures, Kendall's tau, work just fine if you've got holes in the data. So there are things you might have heard, time series methods. Those are parametric methods, and they do not allow any missing data. So you've got to estimate some fudged number to put in there. Often things like just a straight line average between the adjacent two or something like that. So you don't have to do any of that with Kendall's tau. So some missing data, is there a numerical way of assessing it? Not that I know of. It would just be the same. There's no difference between that and any other correlation or regression if you had missing data. That's all I can tell you. There's nothing unique about Kendall tests in that way, which is a good thing, I think. So if you have occasional bottles that break and other things and you want to run a regression, do you not run regression? Well, you would not run Kendall's tau and the ATS line for the same reasons that you would not run regression. But if you would run regression, then there's no reason not to do the Kendall-based procedures. So that's the best thing I can tell you. I'll make this the last one. Jonathan, do permutation methods need correction, such as BCA bootstrap? Thanks. No, generally no. You're not trying to estimate a mean. The BCA bootstrap is an adjustment for bias because what you're trying to estimate is a mean, and the mean is sensitive to skewness, and so there's a bias in the mean. It's all to do with means. In a non-parametric approach, we don't use means. Mean is not a very good measure of the center unless you're interested in mass, unless you're measuring things like flow, and that's what you're interested in on the y-axis. Unless it makes sense to sum things up generally. If you're measuring stuff that it really, summing all the numbers up together really doesn't mean much of anything, then why use a mean? And it has the issues of being sensitive to outliers and skewness. And so the BCA bootstrap is a adjustment because you're interested in the mean. And permutation tests, we're just looking at the frequency of how often a minus 200 in absolute value occurs. Thank you very much for attending, and hopefully I'll be having you on the other end. I can't say seeing you or hearing you. Maybe you'll hear me at least in January. Goodbye.